All right, thank you everyone for coming. Let's get started. It's not about trains, it's about performance. Welcome. So before we get into the talk itself, very briefly, a little bit about me. This is my Twitter bio thingy. I am at David Wengier. I am at David Wengier at most places because of the virtues of having a relatively unique surname. When I was growing up, there was only 4 Wengiers in the phone book. It was my parents, my 2 uncles, and my grandparents. And now, I don't have a phone book, so I have no idea. This is my LinkedIn profile, just to prove there's only ever been one good photo taken of me. This is the extended version, and this is the most important part of my LinkedIn profile. And if you learn only one thing from this talk, let it be this. You can write whatever you want in there, and you can drag it to the top of your profile, and then you can get 8 or 9 of your friends to endorse you, and go get that job you want. But I don't work on Lego. I work at a company, it's a US company. They make mice and keyboards and some software. It's called Microsoft. And I say this as a disclaimer. I wrote the talk before I started working there. The talk got selected before I started working there. So this is merely my opinion on 15 years of experience and not official guidance. But hopefully, maybe it's still pretty good. So let's talk performance. Premature optimization is the root of all evil. Hands up if you haven't heard this little snippet. Excellent. For the record of the video, everybody here is an introvert and didn't raise their hands. Does anyone know who said it? Feel free to. Yes. Knuth, however, I've heard it pronounced many times in his presence, and he's never corrected anyone that I've seen, so I'm not sure. But he said it, and so it's kind of, I think, a bit problematic, or at least how it's used is problematic, and I think it's not what he probably intended. So the way that I've seen this expression used is usually as a way to avoid work. People say it as a way of saying, don't do that work now, don't worry about performance, let there be a problem before you solve it, which is another way of saying let the users find your bugs, which is not great. And the thing is, I think it's misrepresentation too. So I've personally been on the receiving end of this in 2 main scenarios. So say, for example, there's a pull request where someone's written a bunch of link queries, select some, or filter the data, put it into some kind of list, filter it again, do some other thing, call a function. And there's a bunch of these things down the page. And I will come in, and because I'm old, I know how to write for loops still. So I'll say, hey, you could just do one loop and filter that with some if statements or a switch or some functions or whatever. And the reply will be, premature optimization is the root of all evil. Don't have to do any work. Fine. And then the other thing I've seen is the flip side, where I will write some code, and I will write a for loop sometimes, and someone will come in and say, hey, that maybe if you use link, that would be more readable or more linear and not as nested. And my response is usually, yep, that's true. However, personally, I don't have a problem with this, and it uses less memory, and it's probably more performant, but let me know, rest of the team, if there's a readability issue. And then they reply and say, well, no, but premature optimization is the root of all evil. You shouldn't have prematurely optimized it. You should now go do some work because you did the work to do the, anyway. This actually did happen to me. I've had this conversation where someone wanted me to invest more time because I'd mistakenly invested time in their eyes. But anyway, the thing is, it's unfair. So hopefully you're now thinking, Dave knows what he's talking about. You're also thinking he has no idea how to format a slide in PowerPoint. And that's not true. So this is but a fragment of a sentence. And the rest of the sentence and the one after kind of give a lot more context. So the fuller quote there is, we should forget about small efficiencies about 97% of the time, ... Yet we should not pass up our opportunities in that critical 3%. So in his original statement, Donald Knuth is identifying the fact that you absolutely have to sometimes prematurely optimize or care about performance or however you want to phrase it. And I'm going to assume that the 97% and 3% is made up. I don't know. He may have done exhaustive studies. But I think the context here is completely lost on most of the people who spout out this thing. You sometimes have to worry about performance. You absolutely have to. The keen-eyed amongst you will notice that my quotes aren't balanced, and that's because there's another sentence. Turns out he didn't just write one word, one sentence and let it go away. So for even more context, and this is kind of completes the picture for me. Programmers waste enormous amounts of time thinking about or worrying about the speed of non-critical parts of their programs, and these attempts at efficiency actually have a strong negative impact when debugging and maintenance are considered. And so with a tiny bit of poetic license, I think this, so this is a statement I can completely agree with, even though I don't agree most of the time that people spout out premature optimization. Because what he's saying is you have to balance all of these factors, and you shouldn't worry about trying to write the most performant thing first. You should think about debugging and maintenance. And I absolutely agree with that. But I think that same thing applies to all of those other factors of software as well. It's readability and stability and performance. You shouldn't focus on debuggability either. You shouldn't focus on maintenance. You should balance them all out. For bonus points, does anyone know where these two sentences appeared? What paper or what article? Or I don't expect anyone to know. So I just like it because it's a little bit ironic. So the people who say premature optimization is the root of all evil, I don't necessarily rate their broad thinking about the craft of software. And so they also would probably have strong opinions on the use of go-to statements, which is funny because this is from an article titled Structured Programming with Go-To Statements. It's probably a book, I don't know. Anyway, so coding is about trade-offs, right? There is usually a dozen or more ways to solve any problem with code. And so our job as programmers is to work out what is the best way to solve this problem I'm dealing with now. And you have to balance up all of the factors, and performance is absolutely one of them. You shouldn't avoid it. You shouldn't focus on it. It's a balance. And for every situation you're writing code, you have to think about all of the factors. And so you use the context of your code and where you're running, and you use the data and your knowledge of what you're processing, etc., to inform those decisions. And you weigh up the factors and you choose the best path for this specific example. If that wasn't what programming was for, we would have a boring job because we'd just be typing. The thought process is the job. So premature thinking about optimization is absolutely, I think it's a requirement. And that's a bit of poetic license as well, because premature kind of means before you should. Let's say early thinking about optimization. So maybe don't do it, but you have to think about it. You can't avoid it. And you have to, well, you don't have to, but I think it's ideal if you can, create a culture of performance thinking in your organization so that you know when you get to a code review, nobody in your team is going to be saying, oh, don't worry about that till it's a problem, because they will know that everybody else on the team, and you included, have thought about the possible impacts. So how do you think about these things? You have to know the context of your execution. So I used to work at a company that did student software, and most of the customers would have a data dump from their mainframe system that had 100,000 student records in it, and they would send it off to our system, and we cared about 10,000 of them. And overnight at 1 a.m., we'd process that file to see what's changed. And so we knew our code was running at night, in the middle of the night when no one's using the system, and that let us make some trade-offs around performance. If you're writing a website and your code is running on every single request, and it's a public-facing website that could get 2 million hits per minute, then you're going to make some very different trade-offs. So you need to know where your code runs before you can actually identify what is the correct approach. And then you need to know the shape and the size and the type of data your code is processing, if that's relevant. So your code that is running on every single request is probably processing, maybe it's looking at a cookie if it's like an action filter or something. That's a small amount of data. That enables you to make some decisions about what types of storage. Our processing of hundreds of thousands of student records, that's a lot of data. So you've got to make some different decisions. Maybe don't read it all into a string. You've got to validate your assumptions. So I've seen times where people will write their code for high readability, let's say, and there'll be some sort of wasted effort in the middle that could be removed if performance is a problem, but they assume the compiler is smart enough to remove these unnecessary bits and join the pieces up together. And that sometimes is true, but it's sometimes not. And it's really easy to validate your assumptions, especially in .NET where you can trivially decompile your code after the compiler's got at it. But not just that, validate your assumptions about usage patterns. Validate your assumptions about that context, that data. And consider the worst case. So at this previous job with these 100,000 student records, there was a very big university that had lots and lots of money, and was home to some of the best search engines around. And they gave our installation a 5 gigabyte drive on our virtual machine, and they wanted us to process all of their student records, and it was a problem. And I can't remember how much RAM it was, but it was almost nothing. So this thing was constantly paging, and this import over time got slower and slower and slower. So starting out at 1 a.m. when no one's using the system, fine, we can make some decisions and not care about performance as much maybe. But if that import starts to take 8 hours, 12 hours, we're running into people now using the system, or in the worst case, 26 hours. What do you do on a nightly import that takes more than a day to run? Do you run it again and offset your thing, or do you run it twice at the same time, or you just skip a day? So consider the worst case in factoring in those things, and consider how likely that worst case is to happen. Think about your algorithms and your data structures. So think bigger when you're thinking about performance, because it's very easy to sort of go down the rabbit hole and focus on the wrong thing and optimizing the wrong thing. So if we were reading that 100,000 line file into a string or a list of strings, it would be easy to sit there and spend days trying to get this method that processes a list of strings to be as fast as it can be. But you maybe don't want to read the whole file in at once, and maybe that'll help. So think about whether the data structure you're using, there might be a more tailored data structure, and sometimes you've got to go back to your CS stuff if you did CS, which I didn't. But then having said that, don't be afraid of micro-benchmarking once you identify what's actually going on. Because if you can profile your application under the right circumstances, and if you can know what your hot path is, then micro-benchmarking is absolutely the easiest way to make these decisions, because you get really reliable numbers you can make decisions on. And that's kind of what we're going to be talking about. So how do you actually measure performance, or how do you do performance work? And there is only one rule, and I've spoiled it for myself because I just said the word then, but you have to measure. You have to measure your code. You have to measure it before you make any changes. You have to measure it afterwards. You have to compare them, measure it along the way. Measure, measure, measure. That's it. It's number one rule. So this is the code that inspired this talk. I was at work and someone wrote this code, and I was on the pull request, and I looked at it and I read it. And, okay, so data is a list of strings for context. And I looked at this and I aggregate. Okay, I mean, I know link, but I haven't used the aggregate method. I'm going to try to remember what that does, and then empty string. And anyway, what this does is it joins strings together, right? Takes multiple strings, comma separates them. And I left a comment on the pull request saying, don't do that, that's slow and uses too much memory. And as soon as I said that, I kind of thought, that's not really constructive. So A, how slow is slow? How fast does this have to be? Where is this used? How much memory is too much memory, right? You kind of can't really make these statements without some of that grounding in reality. So I decided to find out. So I thought, well, I'll benchmark it, and I'll compare it to what I think is the better thing to do, and let's just see if I'm right. So how do we measure code? This is the first code profiling code that most people write. Does anyone want to shout out what's wrong with it? Because I'm sure that some of you know. Stopwatch, very good. Anything else?
It doesn't factor in jitting.
Jitting, very good. Anyone else? They're the two main ones. There's a few more things. So the easiest way to talk about what's wrong with it is to show you the right way. So this is a better profiler. And there's a few things going on here. So first of all, we are setting the process priority and thread priority to high. And that's just because with benchmarking, you need to measure all of the code, not just find out how long your new code takes. You need to compare it to your old code, and you might have one or two approaches, and you might not be sure. So you're probably going to do multiple runs, and the last thing you want is your antivirus to jump in the middle of one and throw off your results. Or you might be simulating 24 trains running around in Chrome, and it's going to cause problems. So that's a way to just say, dedicate the machine to benchmarking at this time so that it doesn't get interrupted. It doesn't matter what machine it is. I mean, you obviously can't compare my laptop running on battery power to my desktop at home. I'm not going to compare those numbers, but for any one run. So then we call our function, and that tries to take out the overhead of jitting. So .NET is runs in a runtime, it compiles to IL, and then the JIT compiles your code again and optimizes it, and that takes time. So the first run is going to be a little bit slower than subsequent runs. So you get that out of the way. Then we use a stopwatch, as was mentioned. So stopwatch and datetime are both as precise as each other, but stopwatch is more granular. So both of them go down to the tick level, but if you're in a tight loop and you output what the ticks are, you'll find the stopwatch value changes more often. So you want more granularity to be able to profile your code. So always use a stopwatch. It's actually kind of unfortunate that datetime has a ticks property, because I think that leads you down the path of thinking that it's the same. It's not. And then we have garbage collection. In the same vein as jitting, .NET has a garbage collector. You just want a clean slate for your run. You don't want to run your old code, then start running your new code and find that garbage collector has to jump in to clean up all the memory from your old run. You're not going to be able to compare then. So just try as much as possible to get a clean slate for profiling. Then we run our code 100 times to smooth out the spikes, and we output it. So this is the sort of, I don't want to say canonical, but it's like this is pretty good code if you have to write your own profiling code. The thing is, you don't. So the best way to profile code is to use benchmark.net. Let somebody else write the code. So benchmark.net, if you haven't heard, is an open source product worked on mainly by 3 guys, one of whom now works for Microsoft, the other one works for JetBrains, and the other one is currently looking for a job, I think. Might end up at Microsoft, I suspect. But it's supported by the .NET Foundation, so it's it should be around for a while. It's used internally by Microsoft on all of their .NET stuff, or most of their .NET stuff. And it's super flexible. So it can benchmark anything you can throw at it in the .NET world, just about. It can do .NET Full, .NET Core, Mono. You can pick which jitter to use. You can pick x86, x64. You can write your own garbage collector and tell it to use that instead of the built-in one. It's ridiculous. And it's got a whole plugin model, so there's an ecosystem. And it can measure a bunch of different things. So by default, sort of out of the box, you get time, you get memory, and you get the garbage collection characteristics. So I do have a slide here that explains how it works, but I've decided that's really dry, so I'm not going to bother with that. We'll do a demo and I'll explain it live. But that URL, how it works, has an even more in-depth guide, and it actually has pseudocode for the whole thing, which is really, if you're interested, it's a fascinating read. But let's do a demo. I have to warn you though, so benchmark.net is slow. And when I say slow, what I mean is it's thorough, and we'll see why. But so this is the only demo. It only takes about a minute to run, but it's like a minute of dead air is not good. So anyway, let's write a benchmark. So this is a console app. The only thing I've done, packages.config. The only thing I've done is referenced benchmark.net from NuGet and the rest of the world, just to save Wi-Fi, whatever. Apart from that, starting from scratch. So to write a benchmark is really easy. It's a console app. First thing to check is it's in release mode. You have to benchmark in release mode. If you benchmark in debug mode, your results are going to be so invalid that benchmark.net actually refuses to run. It just throws an error. And so to run a benchmark, there's a class called the benchmark runner. If I can type. And we simply say run, and you give it the class that has the benchmarks in it. So that's kicking it off. There's also a thing called a benchmark switcher, which enables sort of console interactivity. So it'll list out the benchmarks. You can pick which one to use. And then now we need to write some benchmarks. And they're written a lot like writing unit tests. So there's a benchmark attribute, which is in that namespace. And then we simply have a public method, and you write your benchmarking code. So we're doing joining strings, right? So let me just create an array that we're going to join together. And I'm just going to be lazy range. Oops. To array. So I just have an array of 10 numbers, nothing exciting. And here I'm just going to join them together with a comma. So there's our benchmark of what I think the good code is. Now, because we always want to compare, we're going to do another benchmark. And this is going to be our old code. So this is aggregate. And if I remember how to do it, aggregate string.empty current next, current plus next. Right. And that's it. We're done. So we can run this and we'll now get results. And I will in a second. One thing to point out that you probably noticed is I'm returning a value from each of these methods. This is something that's just a best practice. It's not required by Benchmark.net, but it's best practice for getting reliable benchmarks. What you want to do is make sure you're using the result of your function, lest the jitter or the compiler optimizes it completely out of existence. And right now, there's not a lot that will apply to in C#, but it's good for future-proofing because they're only working on more of those sort of optimizations. It's particularly if you're benchmarking JavaScript, the V8 compiler is great at just removing code. So make sure you're using your values or you'll get very, very fast runs because the methods don't contain any code. And then the other thing I'm going to do here is I'm just going to mark this as the baseline. And so a baseline just means that we're telling Benchmark.net what our, what we want to compare against. And so in this case, usually, it's the existing code. And the baseline, we'll see in a second, will give us a very simple scaled output. And you can look at your results, and you don't have to read any of the numbers except for the scale. And if it's less than 1, it's better. And if it's more than 1, it's worse. So this is going to run. And as I said, it's a bit, it takes a bit. So I'll talk through everything in a minute. Just, whoops. OK, I won't do that. Magnify sussy. So you can see here it's doing 2 million runs. So the first stage of Benchmark.net is called the pilot, and it does 1 run of your code, and then 2 runs of your code, and then 4 runs of your code, et cetera, to try to find a good amount of runs that's going to give it a nice, reliable sample size to even out the spikes, but not take forever, because it doesn't know what your code does. It could take 10 minutes to run your code, so it doesn't want to run it 2 million times if that's the case. And then it does a series of warm-ups, and it does 2 main warm-ups. One is to establish how long Benchmark.net is actually adding to this whole process. So what's the overhead that it's adding by virtue of its measurement code? And then there's the overhead for the jitter and all of those things we talked about before. And then it does this, which is the workload actual. So this is where it's actually measuring, and you can see it's running our code. So it's running at 2 million operations per iteration, and it's up to 75 iterations. So it's doing a lot of work. It's exhaustive testing. And it essentially does this until it's happy that it's getting consistent numbers it can rely on. So it's doing statistical analysis and all that sort of thing. And you can see what's happening here. We're getting around 300-ish nanoseconds per operation, but there's some here that are like 480, and so that'll be an outlier. And here we go again. So this is, that was running one of the methods. Now we see we're down at 500,000 operations. So this is running the other benchmark. And I'm guessing this is running the aggregate one because it didn't do as much, which means that each one is going to take longer. And you can see they're taking around 700 to 800,000 nanoseconds per operation. So you can kind of look at this and you can see what's going on. We're up to a microsecond. You can kind of guess at what the results are going to be at this point. But if you let it do its work, it does finish. Talk amongst yourselves or ask any questions. But what we'll get out of this at the end is a table of results. Now, I am only doing timing here. The other thing that usually I find I always do in all of my benchmarks is also memory. So how much memory is allocated is a good thing to check. And in this example, it's actually very good as well, but I've got the results in a graph later. So here's the results. We can see string.join, so 358 nanoseconds. And aggregate was 900 nanoseconds. So, more than twice as fast. And there's our scaled output. So we can see our current code is 1, and our scaled, our new idea is 0.4. So it's a clear winner, no-brainer. If I said to do memory as well, it would have ran those same two benchmarks again. So it runs a separate run for each benchmark and a separate run for each thing it's trying to measure. So there would have been 4 runs, which is why I say it's slow. So for just those 2 simple tests, so that was 2 minutes 23 it took. So you would have been out to 5 minutes for comparing 2 one-line methods. So it's not fast, but it's thorough. And to give you an idea, so it's estimated its error there, it's within 25 nanoseconds. The granularity of the stopwatch class on this machine is 300 nanoseconds. So it's able to measure a lot better than it ever really should, but it helps that it ran the code 2 million times. So, whoa, stop zooming. That's benchmark.net. So, some results. So here's the benchmarks I actually ran. And there's a bit more to talk about in this. So first of all, again, much like a unit test, we have our global setup. So this is like a class initialize. And this is where I'm setting up some data. So for the real test, I'm initializing a byte array with random data. This will run once per iteration. So there were 75, 80 iterations, not once per operation. There were 2 million of them. So each iteration is on the same set of data. And then we have this params here with a property. Now, if anyone's used XUnit and used theories, this is basically how the same way. So this is saying to benchmark.net, initialize this property to each of these values in turn, and then run all the benchmarks. And it also runs them for each of the diagnoses. So up here we have our memory diagnoser. So this is saying measure memory as well. So it always measures time. That's saying also measure memory. There's other diagnoses you can add on. And then the rplot exporter is the thing that produces the graphs you'll see in a second. But so with time and memory and 12 values in that params, that's 24 runs of the code times however benchmarks you have, which in this example was 5. So, this was almost half an hour to run this. So you do need to keep that in mind if you're thinking about it. Put a bit of thought in up front about maybe you want to try and run it, not too often. It does take a while. It depends how busy you are. And so then I benchmarked 5 different ways to join strings together because I was curious. So string concatenation, I set that as the baseline because that's the one that, this is like the .NET 101, don't concatenate strings in a loop. It's terrible, right? Well, how bad is it? String builder is then, this is the good way to do strings. So let's see what happens. Over there we have string builder, but I'm initializing it and telling it how big the string is going to be because I was curious to see how much overhead that would save. Then we have string.join and our aggregate. So what are the results? These are the graphs you get out of benchmark.net. You do need to have R installed to get these graphs, but it generates the script that generates the graphs. So if you don't have R installed, you can just run that script once you do get around to installing it. And you get 50 graphs. You get so much data, it's ridiculous. But so these are the results. And it's kind of hard to read, so let's draw a line. So for one string concatenation wins, which makes sense because you're not really concatenating anything. It's only one string. From then on, string builder wins up until we get to 4 strings. And at 4 strings, there's a tiny little bump there. At 4 strings, our pre-allocated string builder with capacity, that one wins because at that length, string builder decides, I better get ready to get some more data, and it initializes a new string builder. So from then on, string builder with capacity wins at every step, but there's not much in it. And so you might look at this and you'll think, well, I'm always going to specify my capacity on my string builders. I mean, look, it wins, it's great. But this is where you've got to know what data you're working with. So this is 1 to 10 strings. If we go to 100 strings, we basically have 3 good methods and 2 bad methods. And our good methods are twice as fast as our bad methods. If we go to 1,000, they're now about 4 times as fast. So we're like exponential growth. If you have 10,000 strings you're concatenating, you can't even see the good methods on the graph, right? So when you're thinking about performance, and this is I hope what Donald Knuth was maybe talking about, don't worry about always initializing your string builders, because if you use either of these 3 methods, it's totally fine. It is so much better than the bad way of doing it that you're probably never going to notice the difference, right? So you've got to know what the data you're working on. If you're working on somewhere in this range, maybe you want to think about it, but I'd actually argue that all of these are close enough to the same. I mean, they're all under, what is that, 1.2 microseconds for 10 strings, you know? So you've got to know how much data. You've got to know what's important, right? Know the context you're working with, know the data you're working with. It is absolutely fine for readability to win, but you want to deliberately choose it, you know? You want to think about performance and maybe measure it and deliberately say, yes, in this case, I will go with the less efficient but more readable way. And maybe put a code in the comment for future people to read that. And then the other thing you've got to be conscious of when you're looking at memory and time is what's more important to you. So the end result of this line of code I saw in a pull request was actually that I was wrong, it wasn't slow, and it didn't use too much memory because it was combining 3 strings of 20 characters each. Actually, it was up to 3 strings because there was some conditional logic. And so string builder, the good way, 120 nanoseconds, concatenation, the bad way, 267. So both methods still slower than I can possibly measure from running the code once on my machine, right? And string builder actually used up more memory because there's a slight overhead to it. So we looked at that code and we're like, well, how often does this run? Oh, it turns out that runs, you know, once on page load and it's a single page app. We just left it. It's fine. But if you're combining 2 meg strings, well, the speed is the same. I mean, it's not the same. It's obviously a lot slower, but you know, proportionally they're the same. But now string builder uses less memory because now the overhead of string builder is being swallowed up by the extra work concatenation does. So you need to know what you're dealing with. If you're on I mean, I don't care about 213 bytes very often, but if I was, you know, writing code for a Raspberry Pi, maybe I would, or I was entering a 640K competition or something. So you've got to know what you want to do. What does slow mean, and what does too slow mean, or what's more important? Let's look at some more examples. Dictionaries. Who likes dictionaries? A very common coding standards thing, and an argument I've had because I personally don't agree with it, is you should always code to interfaces. And I like coding to concrete classes, but we can discuss that later. So here's a benchmark. This one's really simple. Creates one dictionary and then stores it in a field as a dictionary and stores a reference to it in another field as an iDictionary. Never adds anything to the dictionary. These are empty dictionaries. And then the benchmarks, they loop through them, which is, they're empty, so not very long, and return the dictionary just, again, to anchor that code so the compiler doesn't remove it. So there's almost nothing going on here, right? If you use a dictionary, it is twice as fast as using an iDictionary. And it allocates no memory whatsoever, and an iDictionary always allocates memory. And if there actually was something in the dictionary, then these times would slowly, very slowly separate. So even coding standards, you may want to question. Now, this one you'd only do if it was absolutely critical, because this is pretty marginal. But, you know, question your assumptions. I think the people, you would be hard pressed to find someone who, if you had an interview question, said, what's the difference between a dictionary and an iDictionary? You probably wouldn't think, well, one performs better, right? But you kind of got to be open to any possibility. When you actually measure, you might find something interesting. Does anyone know what's going on off the top of their head? Yes, exactly, boxing. So a dictionary's enumerator is a struct. So when a for each loop calls getEnumerator, that returns a struct. When you're using a concrete type, the compiler, you know, knows that it's a struct and the runtime carries that through the whole way. As soon as you go to an interface, everything's out the window and it's always boxed. So the memory overhead is for boxing that struct. So 32 bytes is the object header. And then the time overhead is the time for boxing, but also every call is then a virtual call instead of a call, and it's got to worry about inheritance, and there's null checks, etc. So the dictionary class uses a struct as its enumerator for speed reasons and for memory reasons, and if you then use an iDictionary, you're just throwing them away. So, you know, be aware of what's going on. Loops versus link. This is a good one. I've already told you the answer to this one because I said I'm old and I like loops. Not that I don't like link. I actually wrote a link provider. I love link. It has its place. Okay, so we have an array. We have 10 things in our array, and I'm looping through looking for item number 5. So a simple for loop and a link call, well, link extension method using first or default and passing in our predicate versus using where with a predicate and then a first or default call. This one is interesting just because, I mean, obviously the loop's going to win. I think we kind of all know that, like it's closer to the metal. But the difference between the two link methods I find interesting. And this is another one where we're allocating an enumerator because the where method doesn't do anything, right? It's deferred execution. So it doesn't actually filter your collection until you call first or default, which means it needs to return an object that remembers what your filter was. First or default with a predicate, it just does the work. So there's a little bit of overhead for link, there always is. You've got lambda expressions in the mix. But with the where case, you've got an extra iterator, the where iterator. And then the for loop is bare metal, no allocation, super fast. So this kind of goes back to question your assumptions as well. But the other thing here, like link has other benefits. It is always going to be slower. It was a while ago, so my memory's a bit rusty, but James Newton King tweeted out like a year ago or a couple of years ago, he removed all the using statements for system.link from JSON.NET, and then he just went through methodically fixing the compile errors, and on whatever benchmark he used it ran, it saved 19 meg of RAM. Like, there is an overhead to link, but there's heaps of benefits too. So you've got to be aware of that, and I think we kind of all are. The other one with this example is make sure your benchmarks are real, because, so that code was linked to objects, right? I was looping through an array. With Entity Framework or linked to SQL, where and first or default, they don't really do anything until they hit the database, right? So your results are going to be very different there'll be probably less difference between the two methods. Also, in that case, your database call is going to be way slower than anything else you're worrying about. But so make sure, and this makes it tougher, but make sure if you are curious about this sort of thing, you can't compare link to objects to link to SQL or Entity Framework. You've got to write your benchmark in a pseudo real-world fashion if you want to be able to use the numbers. Last little example, substring versus span. So if you haven't heard, span of T, I think John Galloway mentioned it yesterday or the day before, but it's part of a new set of types in system.memory that allows, it's basically access to the underlying memory behind a string or an array. And it's designed for performance, and it's designed for memory. So no spoilers here, but sorry, it'll be faster. So anyway, we have this code. So this is a very convoluted example, although I'm not sure whether it's more convoluted than looping through an empty dictionary. But we essentially have a string, and then I'm slicing it or substringing it a number of times. So we have our params operator again here. And then we're just parsing this number. And I wrote this because this is sort of, it's not a good example of a parsing library, but it's sort of indicative of the types of work a sort of naive parsing library will do. I know because I've written a couple, and I wish I still had the IP to actually change them, because I'd love to test and see what span does to them. But it's just a bunch of substrings. That's what parsers are a lot of the time. So you'll notice there's two graphs. So yeah, this one's no surprise. Span is faster than substring because that's the whole point. The interesting thing here, so on the left we have the .NET Framework, and on the right we have .NET Core. So this is using Benchmark.NET's ability to run against multiple platforms, which is great. And so this gives you a bit of an insight into how span works as well. And there's a couple of things here. So question your assumption. When doing one operation, somehow span is slower than a substring. I have no idea. I haven't looked into why that is. I'd love to know. I really should. But from then on, span wins. Fine. But if you look, span is allocating some memory for each time it runs, less memory each time, which is, again, interesting. But in .NET Core, span doesn't allocate any data. So in .NET Core, this is 2.1, they have done work to the framework so that they make these new things even faster than before. So they're still better in the full framework, but they're better than better in .NET Core. And then, like each of the operations, the substring operations themselves get a bit faster in .NET Core. That third, when doing 10 there, it should be faster. I'm not sure if that's an outlier. But so the thing here is just to think about, again, what are you running on? What are the quirks of the environment? And there's been so much performance work done in .NET Core that for some types of code, if you can just move to .NET Core and do no other work, you'll get enough of a speed boost that you don't need to worry about your code. Leverage the performance work that Microsoft have done. Don't worry about doing it yourself. And consider if maybe swapping out that framework or component is going to be a quicker win. The best way to improve the performance of any code from any language or any runtime is to remove it, right? So if you can swap out something you've written for something that the framework has written or another component, that could be a quicker win. So you've got to think bigger. And so to bring it back to Donald Knuth, this is my example of the absolute perfect performance story, and I think it is the absolute epitome of what the whole quote of Donald Knuth is. This is from the .NET Framework source. This is the hybrid dictionary class, which I'm assuming no one's used because it's very old. It's before generics. But what this class does is it's a dictionary, and it is a dictionary that changes its backing store from either a list or a dictionary, depending on which is more performant at the time. And the reason I love this is because if you said to me, and probably all of you, hey, can you go and write a class that changes its backing store between a list and dictionary depending on what's more performant, you would, my mind immediately thinks like, well, I don't know, maybe a neural network, I'd time the ads, then I'd keep a history of the last 5 and I'd swap them, but no, 9. 9's the answer. So what they did was forget complexity, forget writing this complicated thing that, hey, look, maybe every now and again it would be better, but way too complex. What they didn't do, though, was throw out performance. They did exhaustive performance testing, presumably using real-world data that they know their customers use, right? And they worked out that if you use a list to store things up until 9 items, and then you switch to a dictionary, you get better performance, right? Dictionaries are slow to look through if you get bucket collisions and things. Lists obviously don't do hashing, right? I love this because I absolutely would have fallen for the trap. I would have written the most complicated code. It would have been terrible. I mean, it would have been fun, but it would have been terrible. And no, 9. It also reminds me of that Dilbert comic, like the random number generator. So to me, this is the epitome. This is what you want to get. You want to solve a complex problem in a simple way if you can, but by being conscious of performance and not by shying away from it. So in summary, should you always use a dictionary instead of an iDictionary? I mean, I think so, but that's just, I will have that debate later if anyone's keen. Should you use structs instead of any of these? No, absolutely no, never, don't ever do anything always. It always depends, right? Every individual thing you do as a programmer is a new decision. The coding standards one, that's maybe debatable, but still, I think coding standards, don't be afraid to question them. They should be a living document. You need to think about every scenario. Developers who want to use the coding standards as a reference guide for how do I solve this problem, I think they'll always be limited in their career prospects, right? You want to be the type of developer that works out, hey, here's a few different ways I could do this. Let me work out what the best way is, or let me talk to other people about what the best way is. So always be thinking about all of these factors. Thank you. There's the thing.